Hey, welcome back to Math with Patrick. Today's October 7th, and we're solving problem 280 from the Daily Epsilon calendar. And today's answer should be 7 because it matches today's date. So, what I see here is a fraction, or maybe a little bit of division, depending on how you want to think about it. And then once we figure out what that number is with division, these symbols right here tell us to floor this function, essentially just round it down to the nearest integer. And then this mod 10 says to then divide it by 10 and finally find the remainder after division. So I wouldn't care what it would be after you divide it by 10. I just care the remainder. Uh, and if you use that logic on, say, like just the number like 73 mod 10, we would do the division, the answer would be 7, the remainder would be 3. Essentially, when you do something mod 10, all you're really doing is grabbing the ones place. So what I see here is that we have some division, and it's going to give us a really large number because like this is astronomically big. And then dividing it by 10 to the power of 25 isn't going to make it that much smaller. So we have a really large number, something in the ones place. I mean, let's just assume it's a 7 because that's today's date. And then I'm guessing, yeah, no, this will be a decimal just because I don't think this number fits into here evenly. So we will have some kind of decimal component. Maybe that'll trail on infinitely. It'll repeat. I don't know. Maybe it'll end again. I don't know. But once we use these little bars here that make us floor our number, we're going to just get rid of all of this decimal part. And then the mod 10 will just pick out that ones place. So ultimately, this question asks, what's the ones place after dividing 10 to the power of 25 by 10 to the power of 25 plus 3? Now, we could just use a calculator. So let me show you what that looks like. So this is what it looks like when I ask an online calculator to do this division for us. Here's the input. And then this is their exact result. It's some astronomically big number. These dots, I think, just tell us that we should just keep reading line by line by line. And then, oh, wait, that's just division. So it's giving us the exact answer, which is the division. And then their decimal approximation here is 9 point, whole bunch of nines. I guess there's a 7 there. And then a whole bunch of zeros. Oh, look, a 9. Some dots, some more zeros, and then times 10 to the power of 1,999. So this isn't the ones place, this 9 at the front, because I would need to move the decimal place 1,999 times over to the right to actually figure out the true ones place. And I don't have enough digits on the screen for that. So I can't really read any of this to really tell you what the ones place is. And so we're a little stuck here just trying to use a calculator. So my new goal is to rewrite this expression in some way where I reduce the absurd value of these numbers. One thing I do notice is that 2025 is a multiple of 25. I think if we do 25 times 81, that gets us to 2025. And so I could rewrite this expression, ignoring those floor bars in the mod 10 for a sec, as let's just do like a plus 3 on the bottom, and then a to the power of 81 on top. Basically, if we just resubstituted like a is equal to 10 to the power of 25, that would bring us back to the original problem there. And then using some exponent rules, we can multiply these numbers, and that would bring us back to 2025. So as long as we keep in mind that a is 10 to the power of 25, we can treat the quotient with slightly lower powers. It's still a little bit hard. There really isn't a good way to simplify this. This plus 3 is putting in a lot of work to make this problem difficult for us. One method I found was to use long division on this. And so we could think about dividing a to the power of 81 by a plus 3. And then usually here you'd want to just kind of write in all of your other kind of terms in standard form, but all of these are just going to be zeros all the way down. Even the last constant term is still a 0. And in this scenario, I would actually use synthetic division. Just that process makes more sense to me. So I would write the root here. Negative 3 would be the root for that factor. And then I would write the coefficients for all of my terms. And so the first coefficient is 1, because I have 1 times a to the 81st. And then all of the other ones are 0. So I'll get 0, 0, 0, all the way down to even more zeros. This 1, again, corresponds to the term with a power of 81. This 0 corresponds to the term with the power of 80, then 79, 78. This 0 would faithfully just be a 0 at the end. So if we wanted to attach some kind of power of a at the end, it would need to be a to the power of 0. And so this 0 corresponds with the term with the degree of 0, and then 1, and then 2. And we have a whole bunch of 0 terms in the middle there. And the process of synthetic division just kind of expedites long division. The process I know is you just drop the 1, multiply with this negative 3, and then you add these two numbers. Of course, it's just a 0, so adding it gets me negative 3. You multiply this and put it here, and then you keep doing this kind of add, multiply pattern all the way until you kind of reach the end. Now we're just basically doing powers of 3, right? This is like 3 to the power of 0, or I guess powers of negative 3. Negative 3 to the power of 1, negative 3 to the power of 2, negative 3 to the power of 3. And so for these last few terms, I want to kind of write it with the same kind of format in like this exponential form. I noticed that this 1 in the 81 sum to, the 1 in the 80 sum to 81. And that's kind of true for any of these entries in this list. So this exponent right here and that 2 should also sum to 81. So I know I can pick back up with 79 being the power here, then 80, and then finally this last one would be a negative 3 to the power of 81. And this spot actually right here would be for my remainder. And from all of this, I know I can rewrite my fraction, a to the power of 81 over a plus 3. I know that this is the same as, and then I would need to multiply, this guy by a to the power of 80. And then the degrees or the exponents would kind of reduce one by one all the way down to 0. So again, this is equal to a to the power of 80. And then I would need to subtract 3 times a to the power of 79. This minus 3 is coming from this coefficient right here. Then I would need to add 9 times a to the power of 78. Essentially now these powers are adding up to 80. So I would get, minus 3 to the power of 79 times a. Again, these powers are adding up to 80 now. I would get plus 3 to the power of 80. I'm ignoring this negative sign because anything to an even power is positive. And then we do have this remainder, which I will write as the remainder divided by the divisor, a plus 3. And so this on the right is going to be some kind of representation of this number here. And all of this is a whole number because a is 10 to the power of 25. So any power of a is going to be another whole number. We're just multiplying and subtracting and adding whole numbers. So all of these are whole numbers. And importantly, all of these numbers are whole numbers whose digits start, I think, in the 26th place. Because all of these have at least an a in them, and a is 10 to the power of 25. And so if I multiply anything to using a smaller power of 10, say 10 cubed, this would just be 9,000. And so this power of 3 kind of shoots this 9 over 3 spots. So it's not in the ones place anymore, but it's 3 spots over, so the 4th digit away. So all of these have an a in it. And so basically the first numerical value I might encounter is in the 26th digit or higher. So none of these terms are going to affect anything at the 25th digit or lower, which is really important because we are on the hunt for the ones place. So the ones place, we're going to get information from just these last two terms. 3 to the power of 80, and then minus 3 to the power of 81 over, and then instead of a, I'll just do 10 to the power of 25, and then plus 3. So let's inspect the ones places of these numbers. We can find the ones place of 3 to the power of 80 by just kind of following a pattern. Let's think maybe exponent here, and then 3 to the power of x there, and make a table. Let's just write a few exponents down like that. 3 to the power of 0 is 1. 3 to the power of 1 is 3. Then this pattern continues with a 9, a 27, and an 81. And here we get a number that ends in 1. And so if we multiplied this by another 3, the ones place would become a 3, and then a 9, and then a 27, and then finally a 1. So for any multiple of 4, I don't really know what the other digits are going to be, but the final digit, the ones place, will be a 1. And so this also works for 80. This is going to be a very long number, but the ones place is finally going to be a 1. So that does give me some information here, where I have a whole long number, and then it ends in a 1. And this is a whole number, and so I'm going to represent that by like some zeros trailing at the end here. Maybe I don't need that many. I don't really know what the tens place is just yet, so I'm just going to put, say, like an A right here, because I don't know what the tens place is. Okay, and we should study this fraction as well. Maybe this fraction is less than 1, right? Because maybe we could have a fraction like this, and if it's less than 1, all of those digits are just going to be contained after the decimal point. Although it is possible that this number is greater than 1, in which case we will have some digits before the decimal point and potentially also after. One thing I can do to detect whether it's greater than 1 or less than 1 is figure out how many digits there are in the number. And like log base 10 actually helps detect the number of digits in a number really well. If we just use it on 100, log base 10 of 100 is 2. Of course, 100 doesn't have 2 digits, it has 3. And so to detect the amount of digits in that, I would need to like add 1 at the end. And then even if we tried a number like 999, log base 10 of 999 isn't going to hit 3 just yet. It's still going to be 2 point something. So if I actually floor this, I'll still get the number 2. And then adding the 1 lets me just get back to 3 because 3 is the same amount of digits as I see in this number here. So if I do log base 10 of x, any number, floor that value, add 1, this will just be the number of digits I have in x. So we can do that to the top and bottom just to see how big these numbers are, to get a sense of whether this is a number that's bigger than 1 or less than 1. Well, log base 10 of 3 to the power of 81, I could maybe use a little log rule here and do 81 times log base 10 of 3. And I don't really know what log base 10 of 3 is off the top of my head. I know it's between 0 and 1, but I don't really know. I guess it's 0.477. So I'll multiply that by 81, and I get 38.6. So using the same kind of method of flooring and then adding 1, I don't really care about that 0.64 at all. I just really care that this is a 38. Add the 1. Okay, cool. Our numerator has 39 digits. And then we can play the same game in our denominator. Log base 10 of 10 to the power of 25 plus 3, floor that, add a 1. This should be really, really close to just 25, because like if this 3 weren't here, it would be exactly 25. And then increasing the argument of my logarithm just by a little bit won't really change my value of the logarithm itself too much. Essentially, it'll be just a little bit above 25. Flooring it will make it exactly 25 again. Adding the 1 shows me that this is a 26-digit number. So this does pose a little bit of an issue. Knowing that the numerator is larger than the denominator by a pretty significant margin, right? There's 13 more digits in the numerator. I know that this number is going to be very large still, and definitely more than 1. And so it's going to contain some digits here, and then also potentially later as well. I don't think this number is going to evenly fit into that one, and I can't really tell on my own. So I'm going to go back and ask the calculator again, and hopefully using this smaller number right here, right, I reduced the power in the numerator from 2025 to just 81. Hopefully this number is small enough that my calculator can give me an accurate result. Back on Wolfram Alpha, we can do this division. Here's the exact result as a fraction, and here is our decimal approximation that we need. Looks like there's a 10 to the power of 13 here, so we would need to scooch this decimal point 13 spaces this way, or we could just look at the mixed fraction version, and here is our integer component ending in 303. So kind of corresponding up here, I can see that our integer component is this 303. And then just for good measure, I'll also memorize those two decimal places, the 7 there, just to see if that might affect our ones place. So this number does end in 303.77. I don't think I need to remember more than that to get an accurate result of what the ones place is for our original number. So back here, doing the subtraction, we can put that 303.77 here, and finally do the subtraction and see what happens surrounding this one digit, or ones digit. So if I wanted to subtract the 1 and the 3, I would need to borrow a little bit. But also, if I wanted to subtract this 1 from this 3, I should also do the place values a bit more to the right. Well, we would need to borrow from this A. Now, A might be 0, in which case I would need to borrow from B. Honestly, B might be 0, in which case I need to borrow from more numbers that way, but eventually I'll find some number that I can borrow from. Ultimately, I'll be able to, cross this off, call it A minus 1, put a 1 right here, essentially calling this an 11. I need to borrow from this, though, and make it a 10. Put that 10 over here, borrow once again, make that a 9, and then finally I could make this a 10. And then doing this 10 minus 7, I get a 3, 9 minus 7, I get a 2. And here's the solution to our problem. This would be forced to be a 10 or a 0, depending on how you're thinking about it. But then finally doing this 10 minus this 3 in our subtraction process does give us a 7 in the ones place. And then whatever happens in the tens place happens. This is just a 0 down here, so we get some digit a minus 1 in that spot, whatever that is. But it doesn't really matter because it won't affect the value of our ones place. So overall, this number right here, once we divide it, we would get something that ends in 7 and then point probably 23, blah, blah, blah. So then flooring it gets rid of all of the decimals, so none of these matter. And then taking this number mod 10 just lets us grab the ones place and only the ones place. So there is our 7. That is our solution for today. And we're all done. So thanks for coming along, and I'll see you tomorrow. Bye.